Hello, this is Miss Moore, and today during chemistry we're going to discuss reaction order. Today's essential question: how is reaction order determined? The rate law. The rate of a reaction, it often depends on the concentration of one or more of the reactants. So that brings us to the rate law. So if we have a reaction where reactant A decomposes into some products, and so I wrote that out here, we've got the rate law. So we have rate equals the change in the concentration of the reactant divided by the change in time. That one you already know. But we can also write that as K, concentration of reactant to the N. So what are all of those things? Well, K is the constant, A is the concentration of our reactant, and then we have N, and N is the reaction order. And we're going to spend a lot of time talking about what we mean by reaction order. So here we go with reaction order. So reaction order, which is the N in the rate law, determines how the rate depends on the concentration of reactant A. Let me write the rate law out again for you real quick so we have it in front of us. Rate equals K, which is a constant, concentration of our reactant, N. Okay, so again, we're speaking about this N here. So if our N is 0, the reaction is called 0 or 0th order, and the rate is independent of the concentration of the reactant. So that means that no matter how much of the reactant you have, the rate is going to be the same. So the reaction is independent of the concentration of the reactant. Okay? If N is 1, the reaction is what we call first order, and the rate is directly proportional to the concentration of the reactant. Okay, so meaning if you increase the concentration of the reactant, the reaction rate will increase. If you increase the reactant concentration of the reactant even more, the rate of the reaction will increase even more. And if you decrease the concentration of the reactant, the reaction rate will also decrease. That's what's meant by directly proportional. And last, if N is 2, the reaction is what we call second order, and the rate is proportional to the square of the concentration of A, or the concentration of the reactant. Okay, zero order reaction. So the rate law for our zero order reaction is rate equals K, concentration of the reactant to the zero order reaction, equals, and that would equal K. So why is that? Well, anything to the 0 power equals 1. So we could have rate equals K to the 1 times 1, I suppose, and that really just equals K. So as you can see, the concentration of the reactant in a zero order reaction doesn't matter. It doesn't change the rate. Okay, so the concentration of a reactant decreases linearly with time, and the slope of the line is constant, which is an indication of a constant rate. And the slope of the line is a measure of K. All right, then we have first order reaction, and in this case, the rate law is rate equals K, concentration of A to the 1. So if you would like, you could rewrite that as it equals K times the concentration of A. The rate of the reaction is directly proportional to the concentration of the reactant. Okay, so if you start with less reactant, the reaction is going to be slower. If you start with more reactant, the reaction is going to be faster. And the rate of the reaction slows down as the reaction proceeds because the concentration of the reactant decreases over time. So up here at the top, you can see we have a lot of reactant, and the reaction's going very, very quickly. When we get down in this area here, we have very little reactant, and the reaction is proceeding much more slowly. And now we have the second order reaction. So in this case, our rate law says that rate equals K, our constant, concentration of our reactant squared. So the rate of the reaction is directly proportional to the square of the concentration of the reactant. So the rate of the reaction slows down as the reaction proceeds because the concentration of the reactant decreases. And in this case, the reaction rate is more sensitive to the reactant concentration than a first order reaction. And you can see that from this graph here that a second order reaction slows down much more quickly than the first order reaction. Okay, because it's more sensitive to a change in concentration of the reactant. Okay, so now we need to learn how to determine the order of a reaction. So the order of a reaction can be determined only by experiment. Okay, and then you can apply some mathematics looking at your experimental data. So we're going to talk about the method of initial rates. So the rate of a reaction is measured for a short time at the beginning of a reaction. So that's why it's called initial rate. It's the beginning. This is done several times with several different initial reactant concentrations. So we try the same experiment over and over again with different starting concentrations of our reactant. Okay, so we're going to look at some data and see if we can figure out the reaction order. There's several ways to do this, to figure out the order. One is to look at the data, and if you can see the pattern, we're good to go. Sometimes some of the data is not easy to look at, so let's see what happens here. So we go from, if we start looking at our concentration of A at 0.1, we go from 0.1 concentration down to 0.2 concentration. So what's happening there? Well, we're doubling the concentration, right? And then again from 0.2 to 0.4, we're doubling again. So now let's see what happens to the reaction rate. We've got going from 0.05, we're doubling, and then from 0.03 to 0.06, we're doubling again. So these change the same, which means we have a first order reaction, or rate equals K concentration X to the 1. I guess we're even using A, not X, right? Let's change that. Concentration A to the 1. Right. We can also determine the order of a reaction mathematically. So what we would do here, let me get rid of this extra writing and start fresh, is we'll write down our rate law, the general form. So we have rate equals K, concentration of our reactant, to the N. So we want to figure out what our N is, right? So what we're going to do is we're going to make a ratio, basically. We're going to do this again. We're going to say rate equals K, concentration of A to the N. And then what we're going to do is we're going to pick two. I'm going to pick this one. So that'll be, we'll call this rate 1, 2, and 3. So I'm going to pick rate 1. So it'll be concentration 1. And I will pick rate 2. So this will be rate 2 and concentration of A2. So we're just going to plug this in. So I'm going to have, for rate 1, we're going to put 0.20 for, whoops. Let's try that again. That's supposed to be our rate, right? So we're going to have our rate 2 is 0.030. equals K, we don't know our K, and concentration 2 is 0.2 to the N. Right, now let's do this for rate number 1. Our rate is 0.015. K, we don't know. And our concentration is 0.10. Oops, I forgot to put my units in here. And now we can solve. So first of all, my K's cross out because they do. Okay, and those cross out. That crosses out. So now when we do the math, we end up with 2 equals 2 to the N. So solving for N has to be 1. Again, giving us a first order reaction. Okay, let's try another one. We need to pick 2. We'll notice that the concentration of M is changing and the rate is changing. So we'll solve for 2 of these. I'm going to pick this time. We'll pick this one as our, well, we'll have reaction 3 to 1 again. And I'll pick these 2. So again, we're going to have rate number 3 equals K times the concentration of A number 3 to the N. And we'll set that up as a ratio. So we'll have, oh, I used the wrong color. We'll have rate number 1 equals K, concentration of A to the 1, N. All right, so let's plug this in. For our rate number 3, we have 0.240. And we have K, and our concentration is 0.40 to the N. And our rate number 1 is 0.015. And we have K, concentration is 0.10 to the N. Let's cross out anything we can. And now we just need to solve. All right, so plugging that into my calculator, on the left-hand side, I end up with 16. And the right-hand side, I end up with 4 to the N. So now, what is that N? How do we get 16? Well, 4 times 4 is 16, right? So we would need to square the 4. So N equals 2. This is a second order reaction. So for this one, our rate law would be rate equals K concentration A to the second. Okay, and we'll take a quick look at this one. You will notice that the concentration is increasing, but the reaction rate stays the same. That means it's a 0th order, so we don't really have to even do any math, right? The reaction date doesn't change, so we're going to have rate equals K concentration of A to the 0, which is basically K. All right. One more. This one's a little bit more tricky because we're going to put 2 reactants in there. Okay, let's try another one. This time you will note we have 2 reactants. We have NO2 and we have CO. All right, so I need to tell you something else about the rate law. So the rate law can have as many reactants involved as necessary. You'll just have rate equals K, concentration of one reactant, which we'll call A, to the N, concentration of the next reactant, we'll call it B, to the M, and that can continue. Okay, so, but besides that, we're basically going to be doing the same thing, although it takes a little bit more effort. So let's go through this step by step. Okay, we're going to have to figure out the N and the M independently. Okay, we have to figure it out for the A reactant and the B reactant independently. So let's, we'll call the NO2, we'll do in blue. So what we want to do is we want to find a time, 2 times, when the one reactant is changing and one is staying constant. So for example, here and here, right? CO is staying constant and NO2 is changing. So in this case, we can figure out the N for, or the coefficient for, or no, sorry, the exponent for CO2. Okay, so we're going to do the same thing we've been doing. We're going to have, we'll call this 1, 2, 3, 4. We'll go ahead and do rate 2 equals K, concentration A 2 to the N, concentration of B2 to the M, and build the ratio again. So we'll have rate 1 equals K, concentration of A1 to the N, and concentration of B1 to the N. All right, so for our rate 2, we have 0.0082, and concentration, okay, can't forget that. And then our concentration of NO2 is 0.20, and that's to the N. And our concentration of CO is 0.10 to the M. And now we'll do rate 1, 0.021, and K, and a concentration of NO2 is 0.1 to the N, and CO is 0.10 to the M. All right, see, we can cross that stuff out, the K's, and we can also cross out our CO's, right, because they match perfectly. All right, so plugging some stuff in the calculator, we end up with, on the left side, I got something like 0.39, etc., which is just about 4. So we're going to call that 4. Equals the right side, got 2 to the N. So now solving for N must be doubled, so N must be 2. So I'm going to put that in here with instead of our N, we'll make it now 2. All right, now we got to do this whole thing again to figure out M, or the exponent for CO. So again, we need to find something where CO is changing and NO2 is staying the same. And that looks like it's experiments 2 and 3. So again, we will have rate 3 equals K, concentration of A3 to the N, and B 3 to the N. I should really not be writing it that way. Let's make this a little bit more clear. K times concentration of NO2 to the N, CO to the M. Oh, and these are the, what is this, the 3's. Okay, and then we're going to do it again with rate 2 equals K, concentration NO3 number 2 to the N, concentration is CO number 2 to the N. Whew. All right, so let's plug this in. Rate 3 is 0.0083. And NO2 at that point is 0.2 to the N, and CO is 0.2 to the M. All right, and then our rate number 2, 0.0082. K, and our NO2 concentration is 0.2 to the N, and our CO concentration is 0.1 to the M. And let's cross out whatever we can cross out. And those can cross out. So now all we have to do is plug and chug. And so when I divide the left-hand side, our rates, you will notice that the rate ends up being about 1, which means there is no change in the rate, which means concentration does not affect the rate, which means our M equals 0. So we have M equals 0. All right, so now we have figured out the order of each of the reactants. Let me get rid of some of this junk. So our rate law would be rate equals K to the A, or we could actually make it a little bit more clear, right? We could say K to the NO2 and B or CO to the 0. But something to the 0 is just 1, right? So we could actually write this as what the rate depend on. Oh, that's not good. Let's try that again. It's really K concentration of NO2 squared, because that's really the only part that's affecting the rate of the reaction. And the total reaction order is a second order. We got that by adding up the 2 and the 0. Okay. And now that you know the rate law for this particular reaction, which is rate equals K concentration NO2 to the squared, you could now plug in a rate at a certain point, the concentration of NO2 at a certain point, and solve for K. All right, that's it for today. Have a good one.